Okay, let's get started. We are going to break down some of the theorems related to chords. Remember what a chord is. A chord is a segment that starts on one part of the circle and goes to any other part of the circle. Sounds pretty basic, but let's see what's in store. Well, this theorem says, look, if you got congruent chords, then guess what? They're going to be the same distance away from the center. And that's what this is saying here. If these two green chords are congruent, then the distances from the center are going to be the same. And the converse is true. What's the converse? The converse says, look, if the chords are the same distance away from the center, then the chords are congruent. So I'm just going to start from scratch and draw a circle on here. And I'm going to put in two chords. This chord and this chord right here. And I'm trying to make them to look the same length. So if I do know they're the same length, they are what we call congruent chords. And if the chords are congruent, then what do I know? The distances, and distance always implies perpendicular, the distances from the center, they're going to be congruent. It's that simple. That's the first of three little nuggets we're going to learn about chords, all right? We haven't applied it to anything yet, but that's our first little theorem. The next theorem in here deals with what? Well, let me highlight it for you. If we have a radius or diameter, and it's perpendicular to a chord, then guess what? It bisects the chord. What does that mean? If we have a radius or a diameter, and it's perpendicular to the chord, then what does it do? It chops these two chords into two congruent pieces. Notice there's one on the left and the right. So once again, as long as the diameter or radius are perpendicular, we are chopping those chords into two equal parts. Here's another example over here. Here's our radius. And as long as we know it's perpendicular, then we know that this portion of the chord and that portion of the chord, they're going to be congruent. All right? That's our second little nugget. Now let's take a look at our third. The third we actually previewed a few days ago, but here it is officially. What's this one talking about? Well, if we're in the same circle or congruent circles, it doesn't quite matter. And it says if the chords are congruent, then the intercepted arcs are congruent. So notice, this is a chord, that's a chord, and that's a chord, and by the tick marks, they're all congruent. Therefore, what do we know? That this intercepted arc, and that intercepted arc, they're all the same too. It's that simple. And the converse is true. What's the converse saying? Well, if the converse says, look, this chord, that arc is congruent to that arc, which is congruent to that arc, then what else happens? Then the chords have to be the same. The converse is like the opposite. It's going in both directions. If the chords are the same, the arcs are the same. And if the arcs are the same, the chords are the same. All right, so here's a little recap of these three little nuggets. The first one we said was what? Well, the last one we just said was what? If the arcs are congruent, then the chords are congruent, and vice versa. If the chords are congruent, the arcs are congruent. The second one we did, well, if we have a diameter or a radius and it's perpendicular, then it's going to bisect the chord. That's a nice little summary right there. And then the last thing was, which was the first thing we covered, was congruent chords are equidistant from the center. So congruent chords are equidistant from the center. If I have a congruent chord over here and a congruent chord over here, then we know what? Then the distance to the center is going to be the same. Well, not only in this diagram is that one true, notice if the chords are congruent, we also know the arcs are congruent. And what else is true? If the radii is perpendicular, then it's going to chop the chords into two parts. So that's like all three kind of lumped together in one diagram right there. Visually, it kind of looks like it's very intuitive. It kind of looks like it's broken into two parts, and it looks like it's perpendicular, and all those things are true. So hopefully you can get a good grasp of those three little nuggets, and we're going to apply them to a couple pictures. Let's try this first one in here. Well, in this case, the goal is to find the radius. All right, so we want to find the radius in this picture. Well, to find the radius, it's kind of tough to do if we don't even see a radius. So no one's going to tell you this, but if you want to find a radius, you got to draw one in. And once again, it's helpful to draw one in that creates a shape that we're comfortable with. So if I draw a radius right here, that is a radius, but I'm not really getting a shape that I'm happy about. And so you got to be a little clever here. It's either I'm going to draw a radius right there, and hopefully you can see what just occurred. We got a right triangle, or you can draw it to point A, and that's a radius as well. So we don't need both of them, we just need one of them. I'm going to stick with this green one right here. So ultimately, that's the R value that we need to see. And notice, this is our line in here that's perpendicular. And if it's perpendicular, we now know it's going to cut this thing in half. Well, look where 24 is positioned. 24 is positioned, that's the length of that chord. And that's going to imply this part is 12 and that part is 12. So that's the little nugget that we just learned about, along with being creative enough to draw in a radius. So I have a right triangle. And so in this right triangle, we've seen this right triangle before. This is the 5, 12, what? That's right, that's the 13 triangle. This is a family. This is a Pythagoras triple in here. You can use Pythagoras to solve for that. You're going to get 13. All right, let's try another one. In this case, what do we see? We see a chord that's 6 inches altogether. This doesn't look like a full radius. It's kind of looking like it's almost a radius. It doesn't quite go to the end. I also notice it's not drawn to scale here. Don't let that bother you. But as soon as I see this is perpendicular, I know this chord gets into two pieces. And so that means this part is going to be 3 and that part is going to be 3. And once again, the goal here, I didn't quite mention that, the goal is to find the radius. Well, this is a radius, but that's not really helping me. So is this one. That's not helping me. I'm going to draw one in over here to A or B. It doesn't matter which one we do, because if you notice, now we have our right triangle. And if I highlight or enlarge this right triangle over here, notice it's going to be 3, 6, and that's my R value right there. In this case, this is not going to be a nice number. This is going to not be a Pythagoras triple. We have to use our knowledge of algebra and solve for this and get some radicals in here. So we're going to have 3 squared plus 6 squared equals R squared. We got 9 plus 36 equals R squared. That's 45 equals R squared. R equals the square root of 45. Then we have to go back to algebra and understand that 9 times 5 is 45. And then this simplifies to 3 radical 5. That is the radius of that particular picture. Let's try one more in here. And so what do we see again? Well, I see a chord. That's 5 units long. I also notice it's perpendicular here. And so this is going to be 2.5, and that's going to be 2.5. It always gets chopped into 2. This is not a full radius in here. It's only 2. And that's what we're trying to find. We're trying to find the radius once again. So I'm going to draw in this radii right there, and I'm going to redraw that triangle. What's that triangle? Well, this is length 2, this is length 2.5, and that's R. Again, you're going to be comfortable with your Pythagoras in here. 2 squared plus 2.5 squared equals R squared. And so let's see, this is 4. 2.5 squared, what is that number? That is, if I'm looking on my calculator, 2.5 and I square it, that turns out to be 6.25. So 6.25 equals R squared. So R squared equals, let's see, that is 10.25. And since I have a bunch of radicals in here, decimals in here, I'm gonna take the square root of 10.25, and I'm gonna take my calculator out, and that tells me it has a decimal equivalent to 3.2015-ish. All right. So once again, we were creative enough to draw an extra line in for the radius. We used Pythagoras, and let's take a small break and then finish up in a little bit.